All right. Good morning, guys. We'll get started. Yeah, it's unbelievable. We are less than 3 weeks now from the end of semester. We should thank God for His gracious offering and protecting us for accomplishing this. Um, so I would like to get started with you guys again. A few reminders. So homework 9 is due on tomorrow by midnight. Okay, so make sure you get started and then finish them by tomorrow midnight. All right. This week we will have our final scheduled lab rotational motions. So this is the final schedule one. And then next week and the final week we'll have makeup. Okay, if you miss any lab, you can come in next week to make up, or the week or the Wednesday in the last week. Okay, now if you are in a Friday's lab section, you can come to the Wednesday section. If you are on the Wednesday's section, you can come to the Friday section. Okay, so just to make your all your missing labs. Okay, if you have more than two to make up. Okay, so and then we'll have our exams 3 this Friday for Friday lab attendees. We'll have exams 3 for the Wednesday extendees on Monday. Okay, and because we'll have exam 3, so on Friday this week, Wednesday's group will just watch the lecture video online by yourself, and then like versa for the Friday group, you guys will be watching it on Monday, the lecture by yourself. Okay, not Zoom meeting. And also the homework number 10 and 12, they will be available online from Wednesday, uh, just from the beginning of Wednesday. Okay, so that's the arrangement for the this week and then the weeks after. Okay, so let's see. All right. All right, so there's a couple questions in the chat. So if you are in quarantine for right now and not be able to take exam, so then you'll make up your exam after you come back. Arrange that with test center, but keep in mind that you'll give a different version of the exam than the class. Okay. So that's for exam 3. If you are in quarantine, that's the arrangement. And then the details, the second question about details for final. Okay, so for Wednesday's lab attendees, you are going to take the final Wednesday, the last week, which let me check, will be the 18th, November the 18th. Okay, during the class time. And then for Friday's group, you guys will be taking it on Friday as scheduled for the final for this class. That will be early time, Friday, November 20th from 7:50 to 9:40. Okay, so that's for that. All right. Okay, so yeah, just let me know if you have further questions. Okay, so we'll get started on the lecture part. Again, we will take quick review on what we learned last time. So last time we check on the dynamics of rotational motion. So this is similar to the dynamics of the linear motion, in which F equal to mass times acceleration. Basically, Newton's second law describes the dynamics of linear motion. So similarly here, you'll use the analog in rotational motion, which is torque equals to mr squared for point mass. That's the moment of inertia times alpha. So tau equals to torque equals to moment of inertia times angular acceleration. That would be the Newton's second law for rotational motion. Okay, and then for moment of inertia, for a system of several objects, if you can consider them as point masses, then you sum the mr squares up for each of the objects. Okay. Now for object that has regular shape, that means you wouldn't treat them as point mass. So for example, if you have a ring, then if it's rotating with the axis going through the center over here, then it's mr square. Okay. For other shapes of object, you can look the moment of inertia up over here in this table. Okay. All right. So then the Newton's second law for rotational motion is tau equal to I times alpha, okay? In analog to second law in linear motion, tau is torque, I is moment of inertia, alpha is the angular acceleration. We also checked the work energy in rotational motion. So again, it'll be similar to what you have in linear motion. So then in linear motion, work equals to force times displacement. In here, you'll be using work equals to torque, which is the analog to force in linear motion, times angular displacement theta, okay? So again, that's similar to linear motion. So then for the energy, kinetic energy in rotational motion is equal to 1/2 I omega squared, okay? 1/2 times I, which is analog to the mass, omega is analog to velocity. So 1/2 moment of inertia times angular velocity squared. So then work energy theorem that's in rotational motion, similarly, it's work equal to change in kinetic energy change. So you will refer to work done in rotational motion as torque times theta, and then change in kinetic energy. This is referring to change in rotational kinetic energy. Okay. All right. We also check on a special case when the object is having the rotational motion as well as linear motion. Okay, at the same time. So this is called the rolling motion where the object rolls without slipping, okay? So then if the object rolls without slipping, then the linear velocity and angular velocity has this relationship, V equal to R times omega, okay? And then V can be calculated as 2 pi R divided by T, which is the period of rotational motion. All right. For a wheel that is rolling, so then it's a combination of linear motion and rotational motion. As a result, the velocity at different parts of the wheel actually is different. Notably, at the point of contact, velocity is equal to 0, but at the top of the tire of the wheel here is twice of the linear motion, linear velocity, okay? Twice of r times omega, which is linear velocity v. And so for the total kinetic energy, if you have object that is having rolling motion, then you should combine the linear and rotational kinetic energies. Okay, so then 1/2 mv squared plus 1/2 I omega squared, which can be rewritten as 1/2 mv squared times a multiple as in the parenthesis here, 1 plus I divided by mr squared. I is the moment of inertia. Okay, and in that sense, if you have an object rolling off a slope, then you can apply conservation of energy, but keep in mind you want to take kinetic energy as combination of linear kinetic energy and rotational kinetic energy, okay? So we were about to check on this problem here. So let's take a look on the solution together here. All right, I'm going to switch my camera here. So this is a real Atwood machine where the pulley is non-ideal. It has a certain mass, all right? But we are going to ignore the friction force here again, just for simplicity issue. And because typically friction force will be very small compared to the weights, okay? So let's take a look here. Two weights here, two masses here, M1, M2. M1 is 5 kilogram, M2 is 3 kilogram. And now there's a pulley here. So M1 is a larger mass, initially placed 0.75 meters above the floor, and you let go of the system. So then M1 will be the descending mass, M2 will be the ascending mass, right? It tells you when M1 just before it hits the ground, or just at the moment it hits the ground, it has a speed of 1.8 meters per second. Now, assuming the pulley is a uniform disk with a radius of 12 centimeters, what's the mass of this pulley? Okay, so let's take a look here. I'm going to draw the sketch over here on my end. So the pulley is somewhere here. All right, M2 and then M1. All right, so this is the initial position of M2 and M1. M1, M2. Okay, now you can imagine that the final position M1 will be hitting the floor over here, and then M2 will be up here, right? So M2 will be here. All right, this is 0.75 meters. I should put this a little bit higher, right? Because this should raise up to 0.75 meters, right? Okay. All right, so in this case, if we ignore the friction force, right, then the only, you can take a look here. So tension over here, there'll be also tension over here. So these two tension will cancel out, right? Then there will be the mg, the weight m1g, there will be m2g on this, right? So then the other forces, they are both the gravitational forces for M1 and M2, right? So for the whole system, M1, M2 plus the pulley, all right, then the energy, kinetic energy should be conserved, or the mechanical energy should be conserved, because the only forces that are doing work is um, the weight, right? The weights, M1G, M2G. Okay, so those are conservative forces. Work done by this tension and this tension will cancel out. Okay, so then you can apply conservation of mechanical energy over here. So we can say U initial plus K initial is equal to U final plus K final. So U is the potential energy, K is the kinetic energy. Okay, we should also include rotational kinetic energy over here for the pulley. So this is, let me call this capital M, and then radius as R, capital R. Now you will have to go back to the table for the moment of inertia for a disk, okay, uniform disk. Moment of inertia for a uniform disk, if you look it up, will be M 1/2 mr square. Okay, the mass times r square. We are looking for this M, capital M. It tells us that final velocity of M1 when it hits the ground, that's 1.8 meters per second, right? So then final velocity for M2 should be also the 1.8 meters per second, right? Because they are connected. All right. Then because the rope goes through the pulley over here, so then the rope should have 1.8 meters per second as the speed, right? So then this guy, for the pulley, the angular speed should be equal to V, this V final divided by the radius, right? This final V is 1.8 meters per second, okay? And then it tells us the radius is 12 centimeters, so you can calculate for the omega, okay? So you'll have final velocity of the two masses as 1.8 meters, and then the angular velocity of the pulley as 1.8 over 12 centimeter, which you want to convert the centimeters into meters first, okay? So in the system, we have M1, M2, and capital M, okay? So let's take a look over here. For the potential energy for M1, so let me call this 0.75 as the h, the height, okay? So then potential energy, if we take the ground level at the floor here, so then for M1, it's M1GH, right? And then for M2, initially it's on the ground here, so that's 0, okay? So you can say M2G times 0 if you want to include everything here. For this guy, for the pulley, because it's a certain height above the floor here. So you can just say, this it didn't tell us what's the height here, but you can say this is capital H. Okay, so I'm going to just say capital H, because you'll figure that it doesn't matter, because the final and initial potential for this pulley there is the same. It's the vertical position doesn't change, so it wouldn't matter at the end. Okay, capital G, capital M, small g, capital H for potential energy of that gas. So this is U initial for the system. All right. Kinetic energy initially the system is at rest, so it should be 0. Okay. 1/2 m1 v1 square or vi initial square, that's 0. This is also 0. And then for this guy, it's not rotating as well, so it's also 0. Okay. Now equals to the final potential energy. Final, you have m1 at the floor, so then it will be m1g times 0, right? Because that's the ground level plus m2g. Now this h, small h of 0.75, and then plus the Pouillet's gravitational potential energy, still that term, capital MGY, okay? So you can see that one and that one will cancel out, so that doesn't matter. All right, plus the kinetic energy of the final for the system. So then you will be having m1 1/2 m1 v final square, right? Plus 1/2 mv m2v square as well. So kinetic energy for m1 for m2, and then plus the kinetic energy for this guy disk 1/2 omega square. Okay. All right. So this is the final potential energy. Okay, a very long equation over here. All right. But you can see these two terms cancel out, and then this one is 0, so that goes away. This one is also 0, and it goes away. Okay. The left hand, now you only have m1gh, right? So you write down m1gh. That's all for left hand. On the right hand here, you'll have m2gh, right? Plus the three terms, plus 1/2 m1v final score, plus 1/2 m2v final score, and then plus 1/2, let me just write it down for right now, omega score. Okay, omega will be vf over r. All right. So let's see. M1gh equals to m2gh plus 1/2 m1v final square plus 1/2 m2v final square plus 1/2 times I. Now you want to express I as the 1/2 mr square because you're looking for capital M, right? So 1/2 capital M r square, that's the I. And omega, we will write down VF times R square. All right. So now this is what you have. And you're looking for this guy. This is the unknown you're looking for. All right. So let's see. If you do squares of this guy, so you are going to square this and then square this, right? So then this R square and then this R square will cancel out. Okay. So then you have 1/2 capital M times V square remaining for the third term. Okay. So the last one will be 1/2 times 1/2 will give you 1/4 capital M times V final square. Okay. Now these two, you can write them down here, plus 1/2 small m2 V final square plus 1/2 small m1 VF square. Okay. And then plus m2GH equals to m1GH. All right. Now look at this equation over here. The only unknown you have is this M, capital M. Okay. So then you can solve for capital M from this equation. Everything else you actually are given with numbers, right? So you can solve for that one. All right. So I think you guys prefer to just plug in numbers here. So and you have number here, and then plug in the quantities with numbers here, and then here and here. Okay. You can keep doing that. That's fine. So I usually would just isolate the quantities that I'm looking for here. Okay. So I'll do that way. So then I'll move everything else, these three terms to the other side of the equation. Okay. Um, so I would have m1gh minus m2gh minus 1/2 m1v final square minus 1/2 m2v final square. That equals to 1/4 capital M v final square. Okay, and then I'll get rid of the factors here, 1/4 and then v square. Okay, so I will multiply both sides by 4 to get rid of 1/4. Okay, so that means this is multiplied by 4, and then I will divide everything by v final square to get rid of v final square on the left hand side. Okay, so then divided by v final square. Okay, then after that I can plug in my numbers. Okay, and then calculate for capital M. So you plug your numbers, 5 times 9.8 times 0.75 minus 3 times 9.8 times 0.75 minus 1/2 times 5 times 1.8 square. Okay, minus 1/2 times 3 times 1.8 square on the top, divided by 1.8 square. Okay, I'm dropping the units because I know everything is in SI unit. Okay, and that equals to roughly 2.148 kilograms. Okay, or you can round it up, round it down to 2.1 because everything is given in 2 digits. Okay, so that's my mass for the pulley. All right, so let me know if you have questions on this one. Okay, before we move on. All right, if you guys are clear, we will take a look at a second example. All right, for our energy conservation here. Now, this one is actually combination of energy conservation in rolling motion with kinematics. Okay, so there are 2 parts of the problem over here. The first part, it says a solid sphere with diameter of 0.175 meters is released from rest. It then rolls without slipping down the ramp over here, dropping through a vertical height. So this is 0.61 meters. And then the ball leaves the bottom of the ramp, which is 1.22 meters above the floor. So when it leaves here, it moves horizontally. It's asking what's the horizontal distance d the ball move before landing. Okay, so we are looking for this distance d over here. All right. So you can also think about how you want to solve for this one, but at the same time, I'll sketch the problem over here. All right, so let's see here. So when it rolls off the ramp over here, it says it rolls off without slipping, right? Again, you will realize then if it rolls down without slipping, then there's no work done by normal force, because normal force is always perpendicular to the surface of the contact, which is it's the direction of a velocity. Okay, so then it doesn't do any work. And then if it rolls off, then the friction force is indeed the static friction. Static friction also doesn't do any work. So then the only work done by would be the gravitational force of the ball. Okay, so then you can apply conservation of mechanical energy from the top of ramp to the bottom of ramp. So I'm calling the top of the ramp to be point A, and then bottom of the ramp to be point B. Okay, so from A to B, then you can apply conservation of mechanical energy. Now from B to C here, let me call the floor here when it hits the floor as at point C. So then this is a projectile motion. Okay, so we will then just take a look at the two parts of the problem here: projectile motion and then conservation of energy. Okay, so let's take from the first part from point A to B. All right, you apply conservation of mechanical energy. Right, which means UA plus KA equals to UB plus KB. All right, now you have a ball that is having rolling motion from A to B. So B is a low point. You can take that as your potential energy 0, or ground level potential energy. Okay, so then UB equal to 0. Then UA is equal to the mg of Y, which is H. Okay, mgh. Let me just use H here because I'm going to use Y in the next part. Okay, so mgh for the potential energy at point A. Kinetic energy at point A should be 0 because it rolls from the top of the ramp down. Okay, so initial, the ball is at rest, or the solid sphere is at rest. Kinetic energy at the bottom over here, KB, you can write as 1/2 mv squared. If you remember, we should include both linear kinetic energy and then rotational kinetic energy. So that means 1/2 mv squared plus 1 times 1 plus I divided by mr squared. Okay, you can go a couple of slides ago to look for this expression, but basically the linear kinetic energy times a multiple, which is 1 plus I over mr squared. Okay, so then you take those terms into this conservation of mechanical energy equation. So then mg h plus 0 equals to ub is 0 plus 1/2 mv squared 1 plus I mr squared. Okay, now for a solid sphere, you'll have to look up in the table for the momentum moment of inertia for different shapes. So for a solid sphere, I is equal to, if you look it up, I is equal to 2/5 mr squared. Okay, so then you'll take this into the I there. So in the parenthesis, then it becomes, so this is mgh on the left, on the right, 1/2 mv squared 1 plus, okay, 2/5 mr squared over mr squared. So that's just 2/5 remaining. Okay, now you can see this m will cancel out this m, so the mass here doesn't really matter. Okay, now you can see h is given, g is the constant 9.8, so then v can be solved. So the velocity at the bottom of the slide, you can actually solve it. Okay, so 1 plus 2/5, that will give you 7/5, right? So 7/5 on this one, and then 1/2, you can put 1/2 in front, and then times v squared to be the other side of the equation, equals to gh, right? So this would be 7/10 times v squared equals to gh. Then you multiply, so you actually divided this guy by 7/10. Okay, that means you are going to do 10/7 on this side. Okay, Then you can take square root, so you can solve for your v in that way. So 10 over 7 times 9.8 times 0.61 meters, and then square root of it. That will be your velocity at the bottom of the ramp, okay? So let me see, that's going to be about 2.92 meters per second. All right. Now you have this velocity at the bottom of the ramp when it leaves the ramp over here, or leaves the table over here. And then it's going to have the projectile motion and then hit point C. All right. So you'll be looking for this D. This D is the horizontal. Okay, so if you look at up the kinematics, you'll see that D is the X direction. So X equals to V X times T, right? So it's basically D is going to be equal to this V times T. All right. So you have the V already, but you don't have the T, right? So then what do? You turn to the vertical direction for the equation of motions, right? So in the vertical direction, it starts from this point and then it goes down. So I intentionally set up the axis to be the horizontal to the left, to the right, and then Y to be vertically down, positive. Okay, so then in the Y direction, Y then is equal to V of Y0 plus V0Y times T plus 1/2 GT squared, because I take downward to be positive direction, right? And then I pick this point to be the origin, so Y0 is 0. And then it says the ball leaves the table horizontally, so that means V0Y is 0, okay? So then you only have Y equals to 1/2 GT squared. Y is the 1.22. So then from here, you can solve for T, okay? T should be equal to 2Y over G and then square root, okay? You guys can do the algebra here. I'm skipping a couple of steps here, but you should be able to figure that out by yourself, okay? So T then equals to square root of 2 times 1.22 meters divided by 9.8 meters per second squared, which will be 0.499 seconds. All right. Now you have your T, you can solve for the D here. So then D is equal to V will be 2.92 meters per second times the T, 0.499 seconds. Okay. So that gives you about 1.46 meters for the horizontal distance traveled when it hits the floor there. Okay. All right. I'll again pause for a few seconds to see if you guys have questions on this one, okay, before we move on. All right. So if you are clear, then we'll move on to the next section of this textbook here. So in this section, it talks about angular momentum and its conservation. So by now, I think you guys have the idea of what's the pattern for this chapter, how it's organized. Okay, so we talk about the angular quantities, then we talk about work energy steering, kinetic energy, and then conservation of energy, and then I think before that we talk about the Newton's second law. Then the next topic in the linear motion is the momentum. So here, then we'll be checking on angular momentum here. All right. So angular momentum, then it should be defined as, so in linear momentum, it's defined as mass times velocity, right? So then in this case, angular momentum, you can see it should be defined as the moment of inertia times angular velocity, right? So we are taking the angular quantities here. All right, so then we just replace the quantities with its analog in rotational motion compared to the linear motion, okay? So this is basically the definition for angular momentum. We use symbol L, all right? And then equals to I, moment of inertia, times omega, which is the angular velocity. It has SI unit of kilogram times meter square divided by second, okay? So kilogram times meter square is the SI unit for moment of inertia. And then per second or radians per second. Radian is dimensionless, so or you can say radians per second or just per second is the SI unit for the angular velocity. Okay, so that gives you angular momentum in SI unit of that. All right. Now for a point mass, if it's moving in a circle of radius r, so then angular momentum according to definition is moment of inertia times angular velocity. For point mass, its moment initial is mr squared, okay? And then its angular velocity is the linear velocity divided by r. So you can see here, so then r, and then this square will cancel out, leave 1r there, okay? So 1r times m times v would be the angular momentum for point mass. Okay, so this is when it's moving in a circular circle of radius r. So in that case, v and r are perpendicular to each other. Okay, so m times v is the linear momentum. So then angular momentum for point mass is equal to r times the linear momentum, just as the other quantities, the velocity and displacement and acceleration, right? When you are having angular quantities, you simply do r times the or actually it's the other way around. So for other quantities, so let me just write them down here. So for delta s is r times theta, right? So v is r times omega, a is r times alpha. Now in this case, actually L is equal to R times P. Okay, so different from those three. Okay, so the relationship over here kind of change that way. All right, so they are different. All right. Now, in general, the R and V are not necessarily perpendicular to each other, or they are not perpendicular to objects, but not necessarily moving in a circular track. Okay, so for example, if the object is moving in an ellipse regarding to an x rotation, so then there will be an angle between I and V. So if I and V has an angle of theta, then angular momentum is Rp times sine of theta. Okay, or RMV sine of theta. Okay, so just keep that in mind. If R and V are not perpendicular to each other, then you'll have a term of sine of theta. Okay. All right, and then this is for point mass again, okay? So let's take a look a quick example here. So this one says find the angular momentum of a 16.0 gram DVD considered to be a uniform disk of radius 6.00 centimeter, spinning with an angular speed of 125 radius per second. And then point B, so point A, you have a disk, okay, which is not point mass. For point top B, you have actually a motorcycle, which you can actually treat as a point mass. Okay, so we'll be looking for angular momentum for a disk and then a point mass. Okay, so basically for a disk, you have to use angular momentum as I times omega, okay, for disk. And then for point mass, you can use R times M times V. In this case, R and V are perpendicular to each other because it says it's a circular track. Okay, if it's a circular track, then R and V are perpendicular to each other. All right. So I think I give you guys a couple minutes to work on this, and then we can take a look at the solution in a few minutes later. All right, so let's take a look on the solution together. So the first one, I equals or L equal to I times omega. It tells us omega. All right, it didn't tells us I. We can look it up. So uniform disk again. So then I will be equal to, for uniform disk, it's 1/2 mr square. Okay, so the L equals to 1/2 mr square times omega. All right, you plug in the numbers. 1/2 times 16, that's in grams. So you want to convert into kilogram, times the radius of 6.00, that's in centimeters. You want to convert it into meters. Okay, so pay attention to the conversion there, and then 125 radians per second. Okay, if you have everything converted accordingly, and then plug in the numbers correct with the correct parentheses in your calculator, you should get 3.6 times 10 to the minus 3. Okay, for this part. For the second part is rather straightforward. You just plug in R, M, and V here. So 35.7 meters times the mass of 125 kilograms times the speed of 8.92 meters per second. Okay, so then that will give you 3.98 times 10 to the fourth kilogram times meter square over second. Okay, that will be the for the second part. So let me stop sharing so you guys can see a larger screen on your side if you choose speaker view. Okay. All right. So let me know if you have questions on this. So if not, then we'll move on here. We'll be checking again dynamics of the rotational motion. So basically, in linear motion, when we check that, we say for the second law, it's better written as net force equal to change in momentum over change in time t. Similarly, over here, if we do delta L over delta t, so the change in momentum, angular momentum over change in time t, then according to definition, if moment of initial is not changing, so then you'll be doing delta W over delta t, okay, which gives you, so change in velocity over change in time t will give you angular acceleration. So then delta L, change in momentum over change in time t, is equal to moment of initial times angular acceleration. All right, and angular I times angular acceleration, we know that's equal to tau, right? Similar to force equal to m times acceleration. So tau equals to moment of inertia times acceleration. Then that's equal to change in momentum over change in time t. All right. So then tau equals to change in momentum over change in time t. So then if you move change in time t to the other side of the equation, it becomes tau times delta t equal to delta L. Okay. So this then it's similar to when we have F times delta t equal to change of momentum, right? The impulse momentum theorem for linear motion. So if we change every quantities into its rotational motion quantity, then we have impulse momentum theorem for rotational motion, which says tau times delta t equals to delta of L. Okay. So let's take a look. This example here, it says a torque. So this is tau of, so tau is equal to 0.12 newtons times meter. It's applied to an egg beater. If the egg beater start from rest, what's its angular momentum after 0.65? Okay, so initial omega is equal to 0. You're looking for L final in the time change of 0.65 seconds. Okay. So in this case, we can apply the delta t, tau times delta t equals to delta L. Okay. The impulse momentum theorem here in rotational motion. All right. So the first part is asking for what's the final angular momentum. The second part is asking if the moment of inertia of the egg beater is given as 2.5 times 10 to the negative 3, what's the angular speed after 0.65 seconds? Okay, so if you have I, find I, that would be equal to, or L equal to I times omega, okay, according to that. So in the first part, you'll be looking for LF. And then once you found that, you should be able to solve for your omega F, okay? So I'll just give you guys a couple of minutes, then we can take a look at the solution together, okay? So you guys can think about how you want to solve for this, or maybe if you already understood it, you can actually solve for it, okay? All right, so let's take a look on this one together. So as I said, this is the impulse and momentum theory in the rotational motion over here. Okay, so we are given tau, we are given delta t, and then that equals to delta L. So tau times delta T then equals to L final minus L initial, right? Now it says the activity was initially at rest, so that means initial angular momentum should be 0. All right, so then tau times delta T will be just your final angular momentum. Okay, so 0.12 newtons times meters times 0.65 second. That will be your final angular momentum. Okay, so 0.078. All right. So angular momentum, if everything is in SI unit, then it's in kilogram times meters square divided by second. Okay, so you can see this is equivalent to newtons times meters times second. Okay, because those are the units there. So those two units are equivalent to each other, but this is your final angular momentum there. All right, now it tells you that in the second part, it tells you that the moment of initial for the egg beater I is given, then you're looking for final angular speed, omega final. So then from here, you can see that final angular speed is equal to final angular momentum divided by moment of inertia. Okay, so it'll be 0.078 kilogram times meter square over second divided by the moment of inertia given as 2.5 times 10 to the negative 3 kilogram times meter square. Okay, so then your final angular speed will be equal to 31.2 in radians per second. Okay, all right, so that's that one there. Let me know if you have questions. All right, so if you are clear, I think I'm gonna just stop here for today. Okay, so next time we'll talk about conservation of angular momentum. Okay, so until then, I'll see you guys on Wednesday then. Bye.